Okay, so I have a series of photographs and slides to get through. There's about 24 of them, I think. This first one just shows phase one of our small wind farm, and there you can see 3 Enercon E33 wind turbines. They're ideally suitable to us in a small island with perhaps smaller shipping arriving and unsurfaced roads and no large cranes to hand, in that they come in a modular fashion. The towers come in 4 sections, which limits the crane size to a 120-ton crane. And the nacelle at the top comes in 3 different sections, the heaviest of which is the generator, weighing at 10 tons, so we can get away with a smaller crane. The capital of the Falklands is Stanley. It was established in 1833. Mr. Khan keeps mentioning that I'm a 6th-generation Falkland Islander. Well, on my mother's side of the family, we arrived there in 1842. So we've been around for a little while. The population is tiny, 2,500. I have a good friend of mine who's an economist, and he says that we are 2 million people short of having a population of 2 million. Our annual power demand is 16 million kilowatts. I put that up there because a similar sized population on a similar latitude to us in Chile, they only require 4 million units. And then there's the military base 31 miles away from us, and they consume 35 million units per annum. Similar sizes of population, very different uses of power. One of the main differences between us and the military is that we have to pay for ours, so everything's metered, so we're very careful about switching things off. Peak demand, which we're going to exceed this winter, is 3.2 megawatts, so for most of you that is very small power demand. This photograph dispels a myth that the Falklands doesn't have trees. Those trees were planted on our golf course 32 years ago. And what I'm really trying to show with this photograph is that there's something pretty nasty attacking that tree from prevailing this direction. You can see it's very windy in the Falklands. This is a photograph taken standing in the south now, and you can see the bowing of the tree trunks with the wind. Trees will grow, but you have to give them a lot of time and a lot of shelter. So you can see it's very windy. This is a photograph taken last November of our power station. Again, it's very small, 6.6 megawatts. You can see our number 6 set there, it's 1,000 kilowatts, and our 2 newest sets at the end, both 1.5 megawatts. We've got 3 generating sets down at the other end, which were installed in 1973 when Edward Heath was Prime Minister. But to look at them, you'd think they were installed yesterday, because we try and look after them really well. You can see it's all well maintained and cared for. But we do need a replacement power station now, because everything's just getting that little bit old. Sand Bay Wind Farm, as I said, 3 Enercon E33 wind turbines. We've now been generating wind power for nearly 8 years, so it's no longer a new idea. We've grown with it. We've had no issues at all on the power side, and we wouldn't be without our wind farm now. We added phase 2, and they came online in February 2010. So again, everything is to scale, quite small. We have 2 megawatts of wind serving Stanley. Where it fits in, this is part of our high voltage schematic. It's hard for me to see, but hopefully you can see this is where our conventional generating sets sit. 8 diesel fueled sets, and there's a connection all the way to Sand Bay where we see our 6 turbines. So all the power comes all the way back in to our generating board, because this is the only place where we have any automatic voltage control. Okay? So if we're 30% wind, it means that every building in Stanley is 30% wind. We do get a lot of visitors, and it does help just to go through a couple of basic concepts. These 3 things have a relationship that if you provide any of the 2, you'll generate the 3rd, and it'll help a little bit later on. In our case, we're a power station, so we want to make electricity, so we have to provide rotation and magnetism. Obviously, we burn diesel to make the engine turn. That gives us our rotation, and we have a device on the end of the alternator called an exciter. That gives us our magnetic field, and we make electricity. The first push bike that I had many years ago had a device that I call a dynamo on the back wheel, and of course in that case you're providing the movement by pedaling, and you've got permanent magnets in there, so lo and behold your lights come on. Every power station in the world uses that concept, whether it's nuclear or coal, whatever. Wind power is a little different in that the movement comes from a renewable source, from wind, obviously. If you've got induction generators, the magnetic field has to come from conventional sources. It imports reactive power from the grid. And this is where some people get a bit disappointed, because without conventional power, your wind turbines aren't going to work. The other type have permanent magnets, tend to be smaller, and we have those that serve our very small farms. And they feed into batteries, and then there's an inverter output from that. We looked at wind power for about 28 years before we did anything about it. And people ask me, Glen, it's very windy here, why didn't you have wind power before? And something that perhaps helps illustrate that is the power output from a turbine is governed by this equation, a half rho AV cube, where rho is the air density. Now that varies throughout the planet depending on temperature and elevation. In our own particular condition, our air tends to be a bit denser. There's a bit more weight behind it. If you play golf in the Falklands, you'll hit a 9-iron about 125 yards. You go to the United Kingdom, you'll hit it 140. There's just a difference. So that's fine. There's plenty of energy in our wind, not a problem. A is the sweep area of the blades. If you imagine the blades spinning in a circle, that's just the area in which they sweep. We've got a lot of wind. We don't need to do anything about that. We've just got the normal blades on our turbines. Problem comes here with not only my spelling of instantaneous. I've got about a 40% success rate. I've got it wrong there, but it's the velocity, and that's in meters per second. And that's instantaneous. That's happening now, and now. And you can see that it's a cube. So for a wind speed, and anyone who's been to the Falklands, I know Kern has, and a couple other people have been there, you have a wind speed of 5 meters per second, you're producing some power. That variable is 125. The wind speed doubles, which it does very quickly in the Falklands, in a few seconds. You don't have double the amount of power. You now have 8 times the power. So this is fantastic. A little bit of wind, you have power, wind speed doubles, you have 8 times as much. Let's cover the whole islands in turbines. This is wonderful. Be careful. A few seconds later, you're down to 5 meters per second again. So now, that variable is 125. You've only got 1/8 of the power that you were trying to do everything with a few seconds ago. So you can see, for small variations in wind, you get a massive amplification and attenuation in power. And for small islands, doesn't matter where you are in the world, that is a big issue. In 2005, I came across the control diagram for the Enercon wind turbine. Hopeless at drawing, but hopefully you can see that that's a turbine. Wind comes across there. It starts generating alternating current. The frequency is between 3 and 7 hertz, depending on the speed of the turbine. But that waveform is hopeless. Nothing you can do with it. It's full of troughs and hollows and rubbish. Yes, we can. The Germans rectify that to 600 volts DC, and then they take a grid reference of voltage and frequency from the system, in our case our diesels, feed it back through a microprocessor and inject it back into the system. The load curve along this axis here is wind speed increasing as you go from left to right, and power increasing as you go up and down. Some people are surprised that at no wind there's no power. Not much you can do about that, or you can't help them very much, but they kick in at around about 2.5 meters per second and begin producing a handful of kilowatts, and then ramp up following the equation we saw earlier, and then they flat line at the rated wind speed of 12.8 meters per second. They continue on a flat line until we reach 28 meters per second, then they go into storm down this line here, where they shut off at 34 meters per second. And if the wind carries on increasing, they just remain off. If the wind decreases, as soon as it gets back into this zone, they'll kick back in. And the Enercon turbine, everywhere else in the world apart from the Falklands and now Ascension Island, who have copied us, follows this curve depending on the wind. This is what they do. What I spotted all those years ago is that we could add a step into the control loop, PS for power station, and instead of that lovely flat line occurring at 335 kilowatts, we could make it happen at 200 kilowatts, at 150 kilowatts, at 120, and I've had it all the way down to 10 kilowatts. Okay? And what that means is you flat line your wind resource. You have time on this axis here, power on that one. So all that our diesels see when we're flat lining is that people have switched power off. Okay? So the diesels take the normal variations that they would anyway, and they're perfectly happy. They haven't have to deal with the volatile nature of the turbine. This is a graph, a drawing of when I only had 3 turbines, 510 kilowatts, and it's useful because for every 17 kilowatts that you import from the wind farm, it's 1 gallon imperial of fuel that you're not burning. So at that rate you're saving 30 gallons of fuel per hour. What we've effectively done is we sail below the wind. We look at our wind and we ignore this bit. We just set our turbines so that that bit of energy, we just allow it to blow by. And it's by not being completely greedy and trying to harness every single bit of wind that we've achieved penetrations which are, for me, still quite incredible. I used to read all sorts of books of wind into diesel, and some would say penetration of 12%, 15%. Others would say if you do this, that, and the other, and load banks and other things, you could get to 20, 25%. But using our own concept and our own idea of not grabbing every single bit, by flatlining the output, we've achieved penetrations of 73%. This is a photograph of our human-machine interface. You can see we've got 6 turbines in columns. Hopefully you can see it. I can't see it very well, but you've got six 6 turbines. You can see turbine 2 is off. You know, I'm not here selling anything. I'm just, you know, they're a machine like any other that have failures or maintenance periods. And at that particular time I took that photograph, turbine 2 was not available. And from memory, because I can't quite see it, I think Stanley was calling for a little over 2 megawatts, and we were 700 odd kilowatts wind, so around about 35% penetration at that time. It's not a special day, it's just a normal day. And down here you can see a window with wind energy converter number 1, and in this window here you can see the number is set to 150 kilowatts, and our watchkeeper can change that number depending on wind speed, load at any time of the day, and the turbine will react within seconds to deliver that power. This is a 2-minute trace of, on the other screen we have, this would be now and this would be 2 minutes ago. Okay, so this gives you a 2-minute view of what's just happened. We have our system voltages sneaking along there, system frequency 50 hertz, and our wind speed. Nothing special about it. I took that photograph to show you 5 of our turbines misbehaving. They're not doing what we want them to do. Apart from this one, just for a brief period, there's enough wind and it starts to flat line. This isn't what we normally want to run them at. And you can see when they're meandering around, it's all rather messy. At light wind speeds, it's not such a huge issue. This is what we're after. Photograph taken a little while later. Again, wind speeds, frequencies and voltages. But you can see our 5 turbines are now flat lining, sneaking along very nicely. I had a group of 4 Uruguayan journalists visit with us, I think about 2 years ago. And as I took them through, we were having very light winds. And just to demonstrate what we were trying to do, I reduced the turbines down to get this flat line. And they came up with a rather lovely expression. They called it peinando el viento, combing the wind, which I thought was terrific. So this is wind energy converter number 6. A lot of information there, but in this window you can see that power available is 330 kilowatts. Power actual is about 148. I can't quite totally make it out. But our excitation current is over 200 amps. The blade angle is 18 degrees. This is how we control the turbine. You set a target number and it will vary the excitation current and the pitch angle of the blade in order to achieve that number. So just to try and demonstrate to you how quickly things happen, this is a 2-minute trace again, and we have turbine 6 along with her sisters producing, I think it's 150 kilowatts, and then I reduce it down to 120, and then it flat lines at 120. And you can see the excitation current has gone down quite dramatically. The blade angle has stayed pretty much the same. So in order to try and capture it in that 2-minute window, I've set it to 120, then back up to 150. But I think that proves the concept that wind power is very intermittent, is very volatile. If it's not blowing, nothing you can do about it. But when you do have it, the technology is there to have it completely under control. This curve shows, and for whatever reason people have quite a bit of difficulty with it, but this is just a load curve for the 2nd of June 4 years ago. Time of day along the bottom, that would be midnight, 1 o'clock. There are 2 curves here. There's a wind and there's a diesel tucked in behind it. All these curves relate to zero. This curve is the total. It's the sum of wind and diesel. So you can see our minimum loads occur, as you might expect, in the early mornings, in the early morning hours, and then it ramps up dramatically as people get up and go to work. And our peak power is somewhere between 11 and 12 o'clock. Because Stanley is so small, everyone goes home for lunch. That happens. We come back after lunch. We're not as keen as we were in the morning, so we don't do as much. But when the school children come around, they're very good. They pick up that this is them at about 4 o'clock, going home, turning on their televisions, PlayStations, all that sort of stuff. And then it meanders down towards midnight. What we try and do with our wind farm is a series of flat lines, depending on what the total demand is. So you can see for many of the hours through the night, wind was higher than diesel. And I might mention this a little later on, that we could have more power through the night. But it's about being fair to the diesels. They need to be well loaded in order to not glaze up and things like that. So you need, our diesels are the most important part of the system, so you need to be fair to them. So we've got about 700 odd kilowatts of wind, and then we try and follow the demand for power. You see it drops back down. What happened there? The wind just dropped. The wind speed just dropped. We didn't have to wait too long. Then we're up to about 1,200 kilowatts through the day, and then as load starts coming down, we adjust everything back. But all this area under this green curve is fuel savings. Okay, some of the facts and figures. We are 33% renewable. Our annual electrical energy, 1/3 of it comes from our wind farm. Our best week was 45%. Our best hour was 950 kilowatts of wind and 350 kilowatts of diesel. And I had to look back about 18 years to find a load lower than that on our system. Fuel displacement value changes all the time with the price. We invested £4.6 million in our wind farm. It's long since paid for itself. Perhaps the most important thing is that we have de-risked 1/3 of our energy needs. We're a small island in the middle of nowhere. We are completely vulnerable to the global price of fuel. And in respect of electrical energy, we are now producing that for ourselves. The next steps for us, we've built a wind farm at Mere Harbour. There's a military base 31 miles from Stanley. Again, it's electrically isolated, but we've built a wind farm there, and it came online at the back end of last year. And the agreement is to sell 4 million units per annum. And from that, what I want to do is use that money, however much of it the Treasury will allow me to use, to buy fuel. So we'll be 33% direct from wind, and then probably another 13% funded by wind. We have 3 flywheel units, which you might have seen on the schematic. We have had 2 really terrific experiments with those, but this is very much research and development between us and Enercon. They have some work, they feel, on the software. We've ran 2 short experiments of a few hours, and the flat line that you saw on previous photos was just completely smooth. Looked absolutely terrific. Very keen in long-term storage. The flywheels would be storage in the seconds and minutes range. We're particularly looking at a battery made by NGK of Japan, and we were talking to them all the way up until the tsunami of a few years ago, and they've pretty much said, look, they've got to focus on their own country for a while. But they make a terrific battery, looks very, very promising, the NAS battery. And what we could do then is, through the night, perhaps store energy to be used during calm periods. Electric vehicles makes a lot of people straight away laugh, because you automatically imagine something that Noddy might drive or something like that. But I've got my eye on something that all of us, the men in the room, would be happy to drive. And they're very, very close. They're very expensive at the moment, but I'm keeping an eye on, in particular, sort of the Ford Focus. One of the limiting factors in the UK or America is the range on a battery charge. They're promising about 140 miles on a full charge. Now, I've lived and worked in the UK. If you go an hour and a half up the motorway, you're not coming home. So that's a big issue. But for us, it isn't. I doubt if I do 140 miles in a week. So you can see the opportunity during the night when we have perhaps spare wind energy. We could use the mobile phone system, or we could use timers to bring on electric cars to charge through the night. And what that would mean is quite differently to perhaps electric vehicles anywhere else in the world that use all sorts of energies to charge up. Our electric vehicles could be 100% green, in that we only charge them when wind power is available, and we see the load from the charge come up, 500 kilowatts. We then adjust our turbines to deliver that energy, so it's 100% renewable. Keys to success for me, and you have to bear in mind I'm talking about our island situation, is that I think I mentioned that we looked at this for 28 years before we did it. We're very proud of our wind farm, and we wouldn't be without it, but we could have had 4 failures beforehand. So it's very important to listen to your engineers. They know what they're talking about, and politically it might be there might be an urgency or a need to do something, and it might be almost anything, but no one will thank you for a failure. And if you have engineering success, the environmental and the economic success follow on. You put any of the others first, you run a risk. Again, in our situation, it was better for the power station is owned by our government, I'm employed by our government, and the wind farm is owned by our government. In that way, the renewable source is used as an efficiency. It's actually counterintuitive for any wind turbine manufacturer or developer to have their power output constrained. They want to deliver every bit of power onto your system that they possibly can, and they probably don't care what's happening to the diesels or whatever else. But if you have one entity, that can be government or private, they will use the renewables as an efficiency, and it makes sense. So in our case, we own the power plant, the distribution, the wind farm, and the future storage. I was in Washington for a battery conference. This is the sort of exciting things I go to. But it was very interesting to see how their energy market works. And I think it works by some miracle, because everything is owned by different people, and there are massive conflicts there and no one really cares very much what each other are doing. Conventional plant for us remains the most important part of the system. We are 33% renewable, which means we're 67% diesel. And without the diesels, nothing happened anyway. And it's probably The only downside from our success really with renewables is that trying to get our politicians and other key decision makers to invest in conventional plant is very difficult. There's tremendous will and enthusiasm for renewables, but a sense of boredom when you want to buy another diesel. Okay, that completes my presentation. Thank you for listening. And thank you to the Association of Engineers, Professional Engineers from Trinidad and Tobago.
Thank you, Engineer Ross, for that very stimulating presentation. Just a point, I saw Justino Jacobs of Glen feverishly taking notes. Everyone should note that these presentations will be compiled and made available after the conference. And I'm certain that at least Justino has, if not one, a couple questions to ask. Floor is open. You need to go to one of the mics, please, and announce your name and company.
Thank you, Mr. Chairman. My name is Prem Nandlal. I'm a retiree. I've worked in the petrochemical sector for close to 40 years. I've worked in the conventional energy environment. And I said, well, what the hell, let me get into the renewables. So I went to UTT, and it is interesting to know that in a couple of weeks, we will have 3 renewable projects going. We will have, the first time in Trinidad and Tobago, a fully energized solar house, 2-bedroom, living room with the normal appliances that a family will have. This, then alongside that, we will be commissioning 2 wind turbines of 6,500 watts each. The third one will come after 10,000 watts. And the reason we are doing that is we are laying the groundwork now for what later on I think will become a necessity for Trinidad and Tobago when more conventional gas runs out. And we are forced to move into alternative energy, one of which is wind turbine. So it is interesting to note how the Falkland Islands have developed their wind alternative energy into the grid. At this point in time, we are off-grid. TNTech has a lot of regulations for private enterprise getting into the grid. Also will be competing with TNTech. So for Trinidad and Tobago, it is interesting to know that we have recognized that, like all the oil-producing countries in the world, even the United States are up to 40% in 2025. They will be up to 40% renewables, combination of solar and wind turbine. And so is Saudi Arabia, Norway, and UK, and Falkland Islands. So, but from a UTT point of view, I think it is interesting the lessons that have been learned by the Falkland Islands. And we will probably approach Mr. Ross for a kind of MOU, a kind of relationship that, based on the experience, based on the criteria you have developed for wind, we can work together to help them to move very fast with wind turbine.
That would be very happy to help.
Thank you for the comment. In Trinidad, we say we have a breeze. Not sure that we have the kind of wind that will generate.
I'm not sure we do either.
So, would you just address that a bit?
Yeah, I think for whatever reason, I think the Falkland Islands is fairly well known for being windy. And our little project has attracted a fair amount of interest and has been directly copied certainly in one place. But I was approached last year to advise the community of Puerto Williams in the south of Chile, and similar sized population to us. They burn, about a quarter of the energy that we do. But as I was passing through, I was happy to help. But very brief research proved that they don't have any wind, and the reason their port was put there was very much for that reason. And so it's incredibly important. It might seem so obvious, but do ask people of whichever island, where there are windy places, but then believe them only a little bit, because people tend to try and help you so much that they will embellish things a little bit. So there's no substitute for measurement. We measured at our wind farm for 5 years before I approached Enercon, and it was 7 years of measurement before we put a turbine up. Measurement doesn't tend to lie, and it will, you can then, most wind energy companies will provide you with the data. If you give them the raw wind data, at Sand Bay, we put up a tower of 10 meters in height and measured wind for a number of years, and passed that data on to Enercon, from which they produced the types of yield that we might expect. But it's so important to get the data right. It's too late after you've invested many millions on a site to discover that, after all, there's only 2 or 3 days of the year when it really is windy. It might seem obvious, and I've only been in the beautiful Trinidad for a couple of days, and it was a little breezy yesterday. I thought my turbines might be producing about 80 kilowatts. So there is some wind there, but there might be another part of the island where there's a significant amount.
Thank you. You have another question?
Hello. I'm Dr. Anthony Green. I'm the Americas Region Chair for the Institution of Mechanical Engineers. I'm from Toronto in Canada. Thank you, Glen. That was a very interesting presentation. But there are a couple of things that I didn't hear you say, which led me to some curiosity. In particular, were considerations given to the location? I mean, you mentioned the wind farm. I only see one solitary turbine of that on the picture. But could you consider the wind direction, wind speeds at various locations around the Falklands? If so, do you have consideration for changes in direction of the axis of the nacelle, the turbine itself, to maximize on the energy equation? Also, in the Falklands, are ecological considerations something that you also put into your analysis? Is there a benefit in being on land as opposed to offshore, as in other parts of the world?
Yeah. Okay, so quite a bit there. Thank you.
Sorry, it's a multifaceted question.
Yeah. We suffer from a small population, but we do have a vast area of land. I think there's about 700 islands make up the Falkland Islands, 2 main ones. And we've got 4,700 square miles of countryside. And land for us is not an issue. I know for some Caribbean islands it is. So effectively, I was able to pinpoint the most advantageous site very early on, away from our mountains and away from any potential turbulence. The Enercon turbine will follow the wind. It will turn. There's an ultrasonic sensor for wind speed and direction, so it will rotate a maximum of 3 turns left or right. That's 2 yaw motors, so it's always pointing into the wind. And the cabling is allowed to twist a maximum of 3 times. If it's done more than 2 turns and it spots that there's a calm period, it will shut the turbine down and unwind itself. Okay, so it's a very clever turbine. It looks like a steel tower with a fan on the top, but I can tell you it's jam-packed full of electronics. It's actually a very elegant turbine, and they're proved over a long period of time. I see Kern nodding, but Kern has visited the Falklands and seen the technology in action, and they've been incredibly reliable in the high 90%. Last year we had some issues, but that was pretty much on our side because of delays with spares. We are where we are. We're a long way away from everything, and sometimes you're affected by postal strikes in other countries. So very reliable, very efficient. We were able to choose an optimum site. The only disadvantage of the site, it was 10 kilometres away from Stanley, and that just meant a cost of about £400,000 of cable. There's a fibre optic cable that links the power station to the wind farm, so you have the SCADA system control and data acquisition, and that's how we control them. It's so important to get the site right. Not everyone likes wind turbines. I have always quite admired them, especially the bigger ones. They have a sort of majestic look to them. But I accept and understand that not everyone does. So my whole philosophy was to find a site that if you like the turbine, you could travel and see them. And if you don't like them, you're not subjected to them every day. There was a full planning process to go through. We're a British government, and it all takes a British amount of time to achieve things. And the only letter of any concern we had came from our Falklands Conservation, and they were worried about bird mortalities, collisions with the blades. And I can tell you we've not had a single mortality in nearly 8 years now, because they're quite a slow-moving blade, and our birds tend to be quite intelligent.
Thank you very much.
You're welcome.
Okay, thank you. In the interest of time, we'll take one last quick question. Dr. Sami?
George Sami from Eco Engineering. I want to start with a comment, please. I was very, very happy to hear you emphasize the importance of data. 40 years ago, when we were trying to choose water source sites with no data, an American colleague made the comment that no Trinidadian likes to collect data because we all like to have opinions. But coming back to your presentation, have you had any situations where wind speeds were high enough to potentially damage the rotors? And if so, what are the protective mechanisms to avoid that?
Yeah, okay. The highest wind speed that we've seen at the height of a nacelle, because that's recorded every second, was 40 meters per second. And again, by Caribbean standards with hurricanes and things, that's probably nothing. But for us, it was quite a severe wind. And at around 34 meters per second, the turbine will shut down. But in addition to that, it has, and I quite like it because it's quite a basic protection system. It's a spring mass damper. So if the rotation of the turbine exceeds a certain speed, the mass overcomes the spring and shuts the turbine down. Also, at the top of the tower, there's a ball that sits in a little cradle. And if the vibrations on the tower exceed a certain amount, that ball will fall out, drop down on a chain, and also turn the turbine off. So not only are they jam-packed full of wonderful electronics, they're backed up by solid, good old-fashioned engineering as well. I have seen pictures of one turbine in the world running away and destroying itself, and that's never a happy thing to see. So nearly 8 years, no problem so far. Okay. Thank you.